All right, so in this clip, we're going to look at an example of setting up a region for integration using polar coordinates when the region boundaries aren't necessarily so nice for polar. So in particular, in this example, we've got these rectangular boundaries here that are not lines where the radius is constant. So it's not like a circle or a radial line type boundary. And so when we're setting this up, you want to think, if I'm doing this in polar coordinates, I'm going to start at the center and I'm going to head outward and I'm going to see where that line, where a radial line like that, enters and leaves the domain. And so you see pretty quickly that it's going to enter the domain on this quarter circle right here, and then it's going to leave on this curve right here, except of course if we chose some other radial line going up in this direction. And then in this case, you can see that it actually leaves at some point along this other straight line. So the first thing that we see is that we're going to have to break this into two integrals. So I'll draw a purple one here indicating where it's going to break. So this is, now using the fact that the dimensions of this are 2 and 2√3, we can see that this is going to happen where theta equals pi over 6. And so we're going to set up two integrals accordingly, one for the lower part and then one for the upper part. Okay, so for that first part, we've got something that looks, and this is not going to be as nearly as pretty a picture, but we're going to be looking at this part down here. And let's see, so the radius is going to start on this one right here. So we're going to have r equals 1 for that curve. Oh, maybe I should make it green just to be like on style. There we go. And then we're going to leave out here. So this is where r equals, and now we have to figure something out. Well, that doesn't naturally look like an r equals type curve, but this is the x, y plane. And in terms of x and y, this is x equals 2√3. And since we're using polar coordinates, and polar coordinates are x equals r cosine theta, y equals r sine theta, we can take this formula and plug it in directly and say, well, that's supposed to be equal to r cosine theta. And so then dividing the cosine over to the other side, we see that r equals 2√3 over cosine theta, or that r equals 2√3 secant theta. So that's going to be the line of exit. So in other words, for our first integral, we've got r going from 1 to 2√3 secant theta, and then whatever our function f is, and then we'll have r dr d theta, and we just need to figure out what the bounds are for theta, and we've got our first radial line going this way across the bottom here, and that's where theta is equal to 0. And then we're going to take all of those radial slices until we get up to this one right here, which we already identified as theta equals pi over 6. So we're going to go from 0 to pi over 6 on that integral. And so that gives us our first part. And now we need to set up the second part. Let me get these out of the way. And so, let's see, boom, 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 something like that. Okay, and so now we're going to be looking at this upper part of this guy right here. And again, we see that the radius starts on this r equals 1, and then it ends on this one right here, which is y equals 2. And so by using this formula right here and connecting these, we get that 2 is equal to r sine theta, or 2 over sine theta is equal to r. So that tells us that we're going to go from 1 to 2 cosecant theta, our function, r dr. And now we have to figure out the d theta bounds. And so here we've got our first radial line in the region right here happens at theta equals pi over 6. And then we keep going zap, 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 sweeping out all of this until we get to this one right here, which is clearly identifiable as pi over 2. So we've got pi over 6 to pi over 2. And there you have it. So that's how you would set this region up for integration in polar coordinates. And so you might want to do this because of the trouble caused by that semicircular boundary down at the bottom, or perhaps because the integrand is something that would be really devilish to try and work with in polar coordinates. You know, some function of this character right here, which is quite simple when it becomes an r.